slight change from our last lecture. We have the same differential equation, but the initial conditions are slightly different. So here's what we're going to start off with. We have an x squared y double prime minus 6y is equal to the ln of x. And then our initial conditions are from y1 is 5 and y prime of 1 is 1. So remember the deal here. We need to find our solution is going to be of the form y is equal to y sub h plus y sub p, where y sub h is the homogeneous differential equation satisfying the initial conditions. It's a solution to IVP x squared y double prime minus 6y is equal to 0, and the IVP, the initial conditions, y1 is equal to 5 and y prime of 1 is equal to 1. Yeah?
So I was doing like the homework. Can you solve for the C1 and C2 first before you
Yeah.
do the
Yeah, so that's probably what we're going to do. So the yp is a solution to the differential equation x squared y double prime minus 6y is equal to ln x, the actual non-homogeneous. But then the initial conditions change slightly. Y of 1 is equal to 0 and y prime of 1 is equal to 0. So the fact that it's a solution to this shouldn't matter to us. Superposition principle tells us that if we add these two together and then we get the exact solution for the IVP. And so the whole point here, though, is that we're going to go through a couple of things. One, we're going to go through the solution to the homogeneous part and then solve for C1 and C2 right here in this first step. And in the second step, we're going to use variation of parameters and Green's theorem. Actually, Green's theorem is the variation of parameters, so we're just going to use Green's theorem, the slightly simplified formula, to help us find the yp. All right, so let's find YH. It should be the same YH as from the last lecture, but let's go through the process. We're going to assume that y is equal to x to the m is your solution, and then we're going to do the auxiliary equation. This is finding y sub h, by the way. I guess we call that step 1. We assume that this is your solution, and then we get the auxiliary equation to equal to, what is it? M squared minus 0 or plus 0 minus 1. So the minus 1m and then minus 6 is equal to 0. So I'm trying to take a shortcut and trying to remember the formula: m squared plus parentheses m2 minus m1, or I'm sorry. Yeah. What? Yeah, it's like if this is a2 m squared plus a1 minus a2 m plus a sub 0 is equal to 0. So that's your auxiliary equation. Your a1, your a2 is 1 in this case. Your a1 is 0. There's no y prime term, and then your a0 is negative 6. All right, so I think we were able to quickly solve for this with m is equal to 3 and negative 2. If we factor or whatever we use, we get this, and so our solution, your YH, looks like a C1 times x to the third power plus C2 times x to the negative 2 power. And then we're going to go ahead and continue to find C1 and C2 right here, right now, to get your Y sub h. So using the initial conditions, when we have 1 in for x is equal to 1, y sub h of 1 is equal to C1 plus C2, and that is supposed to equal to 5. And then we need to take derivatives. So let's put our derivative over here. YH prime is equal to 3C1x squared. And then here the derivative is negative 2 C2x to the subtract 1, and you get negative 3 power. So that when we put 1 in to the first derivative, we're going to get 3C1 minus 2C2, and that is supposed to equal to whatever they have here, and then they have 1. Okay, any way to solve for this would work. Multiply the first one by 2, so 2C1 plus 2C2 is equal to 10. 3C1 minus 2C2 is equal to 1. Let's go ahead and add. That's 5C1 is equal to 11. So C1 is equal to 11 over 5. And put that into any of the equations. C1 plus C2 is equal to 5. We got 11 over 5 plus C2 is equal to 5. And so that's C2 is, let's see, 25 minus 11, 14. So this is going to give us half of our answer. Y sub h is equal to 11 over 5 times y1. Our y1 was set to be x cubed. And then 14 over 5 x to the negative 2. Okay? So that's the first part. Next thing we want is our Wronskian to find the y sub p. So step 2, y sub p. Move off to the next page. Find y sub p. And remember that y1 is equal to x to the third, and y2 is equal to x to the negative 2. All right? So we start with a Wronskian. And the Wronskian is x cubed, x to the negative 2. And then this is 3x squared, and this is negative 2x to the negative 3. And then the determinant is negative 2 minus 3. It's constant, minus 5. That's nice. What else do we need? We need f of t. Let's go back and remember that f of t has to be our differential equation written in standard form. So actually, before we write our f of t, let's rewrite our differential equation. So I'm going to rewrite our differential equation as x squared y double prime minus 6y is equal to ln x. And so if we want it in standard form, the right-hand side will become ln x over x squared. So that is going to help us find our f of t. So f of t is going to be ln t over t squared. So we got our Wronskian, we got our f of t, so we just need Green's function. So Green's function is going to be g of x and y, or x and t, sorry, is going to be a fraction. And the first term is our y1 with t in it, so that's t cubed. Our second is going to be y2 with x in it. And then next is going to be the same functions except switch variables. So we have an x cubed and t to the negative 2. And then we divide by the Wronskian, which is negative 5. All right. So, good so far? So now we want our y particular, and that is simply going to be the integral from x naught to x. X naught is your initial condition x value, which is 1. We'll put that in later. Let me just put the general formula here. This is Green's function times f of t dt. So our integral, let me write it out kind of messy. T cubed x to the negative 2 minus x cubed t to the negative 2 over negative 5 times ln t over t dt. So now let's take advantage of some of the integral properties. The scalar multiple comes out, and then adding and stuff like that. Yeah? T squared, yes, thank you. Anything else? All right, so this has a big 1/5 in it, negative. Let's take out that 1/5 over the whole thing. So that's our constant. Now we're going to have two integrals because you're just subtracting it. The first integral is t cubed x to the negative 2 ln t over t squared dt. Now the fact that you're integrating with respect to t means that the x is constant. So let's take out the x to the negative 2 power out. Let's take that out. And we're integrating from 1 to x. And what's left in just the first term is t cubed over ln t over t squared. Just the first part. T cubed over ln t cubed times ln t over t squared. Okay? So you see that when you do that, the t cubes cancel. I have one t left on top and then ln t. So I have t ln t, no more fraction, dt. So that's going to be an integral that we're going to do. The next integral has, now this is a negative, and then x cubed is constant with respect to the integral that you're integrating with respect to t, so we can take that out. And we're integrating from 1 to x. Now what do we have left? We have t to the negative 2 ln t over t squared. What is that? ln t over t to the 4th. So I'm going to write it as, because I'm going to have to do integration by parts here, I'm going to write it as t to the negative 4 times ln t. That's the same thing as ln t divided by t to the 4th. And I think that has everything all accounted for. The negative 5 in the denominator was taken out of the whole thing. And Yeah, and then that's it. All right, couple of integrals to the side. Let's see if we could do this without using Wolfram alpha. Let's do this integral off to this side over here, integrating a t ln t dt. So I think my u is going to be the ln function. Since I don't know the antiderivative of that, my dv is going to be the t function. So du is going to be 1 over t v, 1 over t dt. And then v is going to be t squared over 2. So this antiderivative here is going to be a 1/2 t squared ln t. Oh, let's integrate 1/2 t squared ln t minus the integral of t over 2. T squared over 2t, so that's just t over 2 dt. So I have a 1/2, and then I'm integrating t, so that's t squared over 2. So I think that's going to give me 1/4 with a negative, 1/4 t squared. So that's the first integral. Second integral is going to require the same set of things that we just did. And so we're going to let u equal to ln t again. And dv is equal to t to the negative 4. And du is going to be 1 over t dt. And then the antiderivative of this, I would need to add 1 to the power, so that's t to the negative 3, divided by that same thing, negative 3. So the antiderivative is negative 1/3 t to the negative 3 ln t minus the integral of, this is t to the negative 3 divided by t. What is that? And t to the negative 4 over 3 dt. Okay. I have a negative. I have an extra negative from the 3. So inside of the parentheses, I have negative 1/3 t to the negative 3 ln t minus minus, so that's a plus, and the antiderivative of this is what? Well, let's pull out the 1/3, and then we have t to the negative 3 again. So t to the negative 3 times 1/3. So let's just make this into a 9, and then that should be it. Oh boy. All right. Oh yeah, don't forget that we have to evaluate this from 1 to x. So when you put x in there, it looks like it's just going to replace t's with x. So 1/2 x squared ln x minus 1/4 x squared. But then you have to also put 1 in there, right? Because this is a definite integral. And when we put 1 into the ln function, ln of 1 is 0. So that makes at least one of them go away. And then if you put 1 in here, you're going to get negative 1/4, right? Put a 0 in front of that if you want, but that's not there anymore. So don't forget that this whole thing is going to be multiplied by x to the negative 2. All right, now the second one, same thing. Let's put an x in there. That just replaces all the t's with an x. Negative 1/3 x to the negative 3 ln x plus 1/9 x to the negative 3 minus, and then let's put 1 in there. Again, the ln of 1 is 0, so that part is gone, and I just have a 1/9. All right, now let's distribute some of these x to the negative 2 and x to the 3rd business and simplify. So x to the negative 2 and x squared is going to cancel. It's just x to the 0. So the first part here will be a 1/2 ln x. This x to the negative 2 and x, that will cancel again, so that's going to leave me with a minus 1/4. And then now I have x to the negative 2 that needs to go to this negative 1/4, so that's a positive, plus 1/4 x to the negative 2. Okay, so that first part is done. And now let's distribute the negative 3 across. So the x to the 3rd, sorry. So negative x to the 3rd, negative 1/3 x to the negative 3. So x to the 3rd, x to the negative 3 cancel. And then you just have positive 1/3 ln x. Now the negative sign carries on in the distribution, and so I would make that into a negative 1/9 times x to the 0 power. And then a negative and a negative will make a positive 1/9 x to the 3rd. Oh, and this whole thing gets multiplied by negative 1/5. So let's do that. So negative 1/10 ln x, positive 1/20, negative 1/20 x to the negative 2, plus, minus 1/15 ln x plus 1/45 minus 1/45 x cubed. Can we simplify anything else here? Oh, we have constants. We have a couple of constants. And we have a couple of ln x's that we can combine, right? So let's take care of that. 15 and 10. So common denominator is 30. So this is negative 3 minus 2, negative 5/30. Negative 1/6 ln x. That takes care of that. The constants, we got 120 and 145. Common denominator, 180 maybe. So 4 for this one. 9 for this one. 13 over 180. And then this. All right. We're rolling now. Are we rolling? Is rolling the right word for this? So now we just have to combine this answer with our other answer when we got the y sub h, right, for the homogeneous. What? Might be wrong. Yeah, I know. All right. So one more page for our last step, our grand finale. The sucky part about this is that it looks like we can combine more terms. Not that it's sucky, but all right, so our final answer will be y sub h plus y sub p. And it looks like we have a couple of terms that we can combine. So let's see if we can combine those two. With the x cubed, I have 11 over 5 minus 1 over 45. What is that? 99 minus 1, 98. 98 over 45. Is that right? That's for the coefficient of the x cubed. The coefficient for the x, we got 14 over 5 minus 1 over 20. So common denominator is 4, 4 and 14, 40, 56, minus 1, 55, 55 over 20. (11 over 4). So y is equal to, let me write it with the y sub p first, 1 over 6 negative ln x plus 13 over 180, and then these constants plus 98 over 45 x cubed plus 11 over 4 x to the negative 2. All right. See if we hold our breath here. Oh wait, I'll hold my breath when I submit because that's a long time. So plus 13 over 180. We simplified everything too. I suppose we didn't have to go through all that stuff, but
Questions
Ready?
No. Oh.
1/36. And 20/9. So 1/36. Where does this constant come from? Let's trace it back. One over 20 plus 1/45. What's that? (13/180). Positive. Positive. The antiderivative was here. (1/9). Negative, negative. Let's hit the positive. And there was a negative in front here that we distributed. So that became negative. About the 1/4, does that come out right? So this thing with a minus sign. All right, so that's the origin of those constants. And which one else? What else was wrong? X cubed. What was that? So the x to the -2 looks like it's okay, which means it should be this integral that we're messing with. That has negative, negative, negative. We kept track of the negatives, right? They went to the right places. So UV minus VBU It has to be somewhere over here. B du is negative, so it should be plus. Distributed becomes a minus. Oh boy, I don't know. Anybody see anything? Hey, your computer's wrong, huh? All right, well, if you find my mistake, I'll give you 1 point on the test. You can Wolfram alpha it, but it's a bunch of little pieces here. So yeah, 1 over 36 is that last number, the constant number. We had 13 over 180. So we had 15 here. What's 15 divided by 180? How do you get 36 out of 180? 12. So this has to be a 12 here. 12 divided by 180 is 1 over 36. So how many times does 36 go into 180? 5. So it should be 5 over 180. And our other constant has a 9 and 20. So divide by 5. So this should be 100 over 45, right? So 5 over 180 and 100 over 45. Yeah, it's 20 over 9. So it is 100 over 20. So we need 100 over 45 in here somehow, and we need 5 over 180 somehow. Okay. Off by something. So if you guys can find it, I'll give you a point on the quiz, on the test. We need to at least introduce the boundary value problem. So let's throw that in there. Maybe we should. Yeah. What were we supposed to talk about today, anyways? We're still talking about Green's function. All right. Let me just, I don't have my file open. Let me introduce the boundary value problem that will require a different Green's theorem or Green's function. So for a boundary value problem, we have a slightly different Green's function set up. And the boundary value problem has two possible x values. So what they do there, instead of setting up your Green's function a certain way, is that they split up Green's function into being able to handle the first part of the boundary and then being able to handle the second part of the boundary. And what's going to happen is that you're going to need one of your fundamental solution functions to be to satisfy the first part, and then your other fundamental solution function to satisfy the second part. So for the boundary value function, you have the same sort of differential equation, except your boundary conditions, instead of IC initial conditions, you have boundary conditions. Your boundary conditions are y of some first boundary is equal to 0, and then y of a second boundary is equal to 0. And instead of having the same x value for your initial condition, for the boundary conditions we have different x value, or different x values. I think they want this just to be zeros. Not 0, 0, but A to B. Yeah, so your A and B are your x values, and so your x values are going from A to B. And so the idea is, where does x come into play here? Well, x is going to come into play as an integral in between them. What does that mean? Well, Green's function is defined slightly differently. And the way Green's function is defined, we'll actually see that our integral is going to be integrated from a to some x value, and then we'll be dealing with half a Green's function, and then the other half of Green's function will be taken when we integrate from x to the upper limit b. So what's going to happen is that your integral is going to be an integral from a to x of this first function, y1 t y2 of x over wt times f of t again. And then you're going to integrate from x to b of this second function, y1 of x, y2 of t, over the Wronskian times the function t dt. All right? So, you do have homework on this stuff that's going to be due not this Sunday, but the following Sunday. So what I'm going to do is I'm going to make a video of an example of doing this particular type of problem, and then when we come back on Tuesday, we'll just briefly 5 minutes talk about this this stuff, and then go on to the next chapter. Because we need to get to the next chapter to be able to take your exam. Okay. All right, so we'll leave it at that. Oh, if you find find my mistake somewhere along the line, try to print out my notes, which I'll have sometime by the end of today, and then try to circle or figure out exactly where that mistake was made, and then take a picture of it and send me an email. Okay, so the first one that gets to me gets the point. Probably not. We'll see. All right. See you guys on Tuesday.